Thanks for being here. My name is Pedro, and I just started my second year of my PhD at Philip. And today's presentation is a bit about, so because of that, I'm about to present my TRP, my thesis research plan. And today's presentation is mostly about that, not exactly the same presentation I'm gonna do, but more or less a bit about my work, about the context of my work, and also some preliminary work I will be doing. So just an outline, I'll introduce the context, some objectives, some concepts to make sure everyone is on the same page, also the preliminary work and some future directions. Okay? So first of all, my work is on medical imaging. More specifically, I'll call here disease management. So this high-level view of these, let's say, these three stages in medical imaging analysis. So I call here early stages is about screening, lesion detection, tumor localization. My work is not about that. So it's more about characterization and monitoring. So the tasks are also relevant, but the applications are also relevant for my project. More about characterization, but also monitoring. So it's about, I only have malignant cases. So it's not about, for instance, classify a tumor as benign or malign, like malignant cases. I only have malignant cases. It's more about the process of a person that already has the disease. So to improve this process. So some objectives of my work. So I defined three main challenges. It's about annotated data. You guys know that it's not easy to collect medical data well annotated, and even more when I need more details. Like it's not enough to say it's a malignant case. I need to know the mutation status. So this person has this type of breast cancer and has mutations in genes A, B, C. So it's important this level of detail. So it's even more harder to collect data. They usually are imbalanced, and also interpretability. You know more than me about that. And I have two main points of my work. Is about data efficiency and promoting interpretability using image-based features. Okay, so if I could summarize my work is on these two main topics. And so I didn't talk about my title. It's quite a long title. Just to give a context, I applied for FCT scholarship, and so I stated the same problem, and I wanted to say exactly how I would tackle this problem. So I defined these three multitasking, semi-supervised, and interpretable machine learning. But now I want to be more. I won't be restricted to these methods. So I'll change that. I'll handle this in the future. So I actually want you guys to know that my actual focus is on data efficiency and to some extent promote interpretability in the context of disease management. So I want to bring some concepts before talking about the preliminary work. Pretty sure everyone already heard about radiomics. And just to make sure everyone knows what it is, some of you already worked with that. So in biology, there is the suffix "om." It's a reference to the complete set of elements in a system, and omics is the stud of these sets of elements. As an example, genome is the complete set of genes and organisms, and genomics is the stud of our sets of our genes in an organism. I'm saying that because when we bring to medical imaging, more specifically to radiology, we have these radiomics. That's basically about extractive features from our region of interest. Usually it's a tumor, so extractive features from a tumor. And these features are like the shape. So if I say this tumor has a volume of whatever, this is a radiomic feature. So usually these features are shape, so they are about shape or texture. Okay? And when we link these images to molecular genetic characteristics, it's radiogenomics. So it's basically as simple as that. And a bit more specific, I have a main data set. It's on breast cancer, MRI, but I'm not restricted to this data set. So it's more like I know I can do a lot of stuff with this data set. So if everything else goes wrong, at least I know I have this, and I can work on this data set. And so just to give a context, breast cancer is classified based on these three biomarkers: estrogen, progesterone, and HER2. So, and they are related to prognosis and treatment decisions. So it's important to know they are assessed in a clinical workflow, but usually not from MRI. And the data set I have is composed by 922 patients and only MRI. Just to give you guys an example, this is a MRI from a patient, and what I have for the three biomarkers. So they are quite imbalanced, more or less a ratio of negative to positive of 1 to 3, 1 to 2, and 5 to 1. So more or less the proportion. So talking about one of the preliminary work I did, it was just accepted to a conference, and it was my goal was to evaluate the predictive performance and complementarity of these three approaches to this problem. So usually the works on this field, they do one of these three approaches. So what I call here handcrafted is exactly what I said about radiomics, just a different name for the same thing. And so, or we have deep features. So it's using a pre-trained encoder, a deep learning model. So usually a frozen encoder and extractive features. So they are more abstract, and what I call here machine learning pipeline is about resampling because of the imbalanced data, dimensionality reduction, and the machine learning model like the rainforest, SVM, these well-known methods. So my goal was to evaluate, because usually the works do one of them, I wanted to evaluate how they, in a same setting, what I get individually and also in combination. So what I did, so for handcrafted features, we have this library in Python, this Python library called PyRadiomics. They have predefined equations. So basically, when we have here, like what I call here, the volume, the texture, end of the day, these are equations, so predefined equations, and they have all of these already implemented. So it's just using a Python library. And for deep features, there is this framework, MONAI, maybe some of you already heard about it. They have a lot of resources regarding medical imaging, but I used it more specifically these 5 ResNets that trained on medical data sets. So they have this is what matters for this context is these 7 variants trained on medical data sets. So this is what I evaluated. Just standard well-known methods for resampling, for dimensionality reduction, for the machine learning models. Also for deep learning, entropy, for colloids, and how initializing the models. So the only difference here is pre-trained. I freeze the weights and fine-tuning. It's transfer learner, but fine-tuning the weights. So what I did was these 6 experiments, this setup. So only had so using only handcrafted features, using only deep features, combine them before the machine learning pipeline, so early fusion, or at the prediction level, only deep learning pipeline, and combining also the predictions from machine learning and deep learning. So it was to try these 6 experiments on the 3 biomarkers. So that's the results I got. These are AUC values, the top 3 AUC values for each experiment, for each biomarker. So they are totally, they are not related to each other. So it's just, so I have 18 possibilities. So I ran the 18 setups. So I ran all of these 18 times, so they are not related. The goal is exactly to see if I could find some pattern among them. And for this data, for these results, I'll just highlight 2 things here. So something I want to check if any type of feature is better than the other, but it's not always the same. For instance, for estrogen and progesterone, I had better results for handcrafted, but not for HER2. But for all of them, I had better results using late fusion. So that's one of the takeaways about this work. But what for me, as I said, this is a preliminary work. I mean, I don't want to propose like late fusion, always use late fusion, or always use SMOTE to resample. It's not what I want from this preliminary work. The main point is actually it was get to know better this data set that I'm gonna use throughout my PhD, and also to have a starting point for the next experiments. For instance, the majority of these results was using either HasNet 10 or 18. So for instance, what I'm doing now, I'm using HasNet 18. So now I have, so I know how I start because so I have some criteria because some experiments I did, and this is it was more exploratory study. Okay, so that's all what really matters for me about this work. Also, yeah, something useful also for me is, although late fusion did improve it a bit, they are still biased to the majority class, so that is still a problem. Oversampling had a limited effect. Like most of these results didn't use resampling. So, and also in dimensionality reduction was useful. It was expected. Like I have a lot of information about only a tumor region, so it's likely to have like correlated features or features we can remove. Just to finish this presentation, some stuff I'm doing right now is about multitask learning. As I said, I did these 3 tasks separated, but now I want to do the in combination. So using trying to predict the 3 together. What I know from the biology perspective is that estrogen and progesterone, they are related. I don't know much details about the biology, but what matters is they are related. So maybe I can use that for my model. H2 is more independent, but maybe they could share some representations. And so I could, something I'm trying is exactly like to translate this domain knowledge into the model, into the experiments. And also, as I said, I'm not restricted to multitasking and supervised machine learning. Yeah, an example is the Chimera challenge. Philippe and Leonardo just participated in this challenge, and it's about multimodal learning and to predict recurrency risk. So but it is part of my PhD as well. A bit different what I stated in the beginning, but in the title, but it is also part of my PhD. Also, semi-supervised, incorporate domain knowledge, more or less a bit what I plan to do in my project. And that's all I have for today. Thanks for being here, for the attention, and I'm open to questions and even more to suggestions.